Ministral 3, parameter-efficient AI via Cascade Distillation.
Yeah, today we are diving straight into the Ministral 3 series. This is a brand new family of dense language models, and they're specifically engineered for anyone with compute and memory constraints. A huge step for open weight efficiency.
The core insight here is genuinely novel. Ministral 3 gets really competitive performance across, three different sizes? 3B, 8B, and 14B parameters.
And they do it by using this iterative training strategy they're calling Cascade Distillation.
Right. This is their way around that massive data wall we see everywhere else.
I mean, they essentially start with a powerhouse, the 24 billion parameter Mistral small 3.1, and then just progressively shrink it. They use iterative pruning and continued distillation.
And the efficiency metric is, it's critical for the industry. These models were trained on only 1 to 3 trillion tokens.
Which sounds like a lot until you compare it.
Exactly. When you look at foundational models like Llama 3 or Qwen 3, they used 15 trillion and 36 trillion tokens. So this token efficiency is, it's staggering. And yet the models are competitive. And crucially for you, the developer, they've released all 9 variant-based Instruct and reasoning for each size, all under the Apache 2.0 license.
And every single one has image understanding capabilities built in, so it's an incredibly flexible resource.
Okay, so let's really unpack this core innovation, this Cascade Distillation. The sheer cost, both in compute and data, of modern LLMs has pushed training budgets into, the stratosphere.
If you're not one of the big labs, you just can't play that game. You need a different strategy.
That's the problem statement, right?
Yeah.
How do you get performance that's even comparable to models trained on orders of magnitude more data, but you're stuck with a budget of just 1 to 3 trillion tokens?
The answer has to be efficient knowledge transfer.
And that's the recipe Cascade Distillation provides. So instead of just throwing huge amounts of data at a small model and hoping it learns,
you're transferring knowledge from a larger, already competent parent model. So walk us through that iterative process. What does it actually look like?
It's this progressive 3-step loop that moves downward in size. Prune, distill, repeat. So they start with the 24B Mistral small 3.1 parent.
Okay.
They perform a surgical pruning operation on it to create the 14B student. Then they distill the knowledge into that 14B student using their entire data mix.
And once that's done, they just do it again.
They just do it again. They prune the 14B model down to create the 8B student, distill, and then finally repeat that whole cycle one more time down to the 3B model.
That just sounds so much more FLP efficient than training 3 separate small models from scratch. Are you also avoiding things like catastrophic forgetting?
Precisely. The paper says it's significantly more FLOP efficient because that parent model, it already holds all the foundational knowledge. And it avoids data repetition.
Because you're doing it all in a single pass through the data.
Right. They're progressively shrinking the model and then just continuing the training. The entire end-to-end process uses their data mix in one single run. You're not paying to retrain on the same data over and over.
And the results seem to prove it worked. They highlight that the Ministral 314B base model performs, almost identically to the parent model that's 40% larger?
Yeah, it closely matches the Mistral small 3.1 base. It's a huge validation of the whole strategy. It shows that so much of the core knowledge in that 24B teacher was either, redundant or could be compressed.
And that they successfully transferred it into the smaller student.
Exactly.
Okay, before we get into the really deep mechanics of the pruning, let's just quickly touch on the foundational architecture. It's shared across all 3 models, right?
Yep. They all use a standard decoder-only transformer architecture. It scales pretty predictably in depth. 26 layers for the 3B, 34 for the 8B, and 40 for the 14B.
And they're using established high-performance components.
Totally. Grouped query attention, GQA, with a configuration of 32 query heads to 8 KV heads.
Okay, so that's standard modern fare, plus ropey positional embeddings, SWIGLU activation, and RMS norm. I did notice they committed to a very large vocabulary, 131K tokens across all the models. Why is that specific detail important?
Well, that large vocab size is just critical for versatility, especially in an open source model. It lets them handle diverse scripts and, tokenization nuances much more robustly.
Yeah.
It's about making sure these small models aren't bottlenecked by their token set.
Right. Now, here's where the engineering gets really sharp. Context length. They got up to 256K tokens for the base and Instruct models. That's massive.
It is, and it definitely didn't happen by accident. They combined 2 specific techniques. The first is yarn, which is a pretty common strategy for scaling rope-E embeddings.
And the second?
The second is a more subtle detail. Position-based softmax temperature scaling. right inside the attention layer.
So by using both of those together, they can generalize the positional embeddings to those enormous lengths without creating instability or having performance drop off at the edge of the window.
Exactly. And we shouldn't overlook the multimodal part. All these models have built-in image understanding and is powered by a 410 million parameter vision transformer, a VIT.
But the efficiency trick here is that the VIT itself, which is a big component, is just copied from the parent and then it stays frozen during the entire training cycle.
That's right. They throw away the original language vision projection layer, and they only train a new, smaller projection layer that's tailored to each of the 3 different language model sizes.
So you save a ton of compute, but still get the visual input properly integrated.
Yep. And speaking of tricks, there was one specific optimization just for the smallest model, the 3B version.
The tied input-output embeddings.
Yes, because that 3B model is so tiny, just 26 layers. If the input and output embeddings were separate, those parameters would just dominate the total parameter count. It would make the model really inefficient.
So tying them together is a necessary constraint to keep it effective at that small size.
A clever move.
That makes perfect sense. Okay, so the architecture is the skeleton, but the real engine here is the pruning process. Let's dig into how they decide what to cut. They're not just hacking away randomly.
Not at all. The goal is always to remove parameters in a way that minimizes the change in the model's internal representation. So the first step is layer pruning.
And how do they score a layer's importance?
They use a pretty straightforward proxy, the ratio of a layer's input to output activation norms. They found this simple ratio was actually a really strong indicator of a layer's overall contribution. They just prune the ones with the lowest scores.
Okay, so they cut entire layers. Next, they tackle the model's width with hidden dimension pruning, and this involves principal component analysis, or PCO.
Right, and this is a great example of applying an advanced technique very practically. They don't run PCA on every single layer separately. Instead, they concatenate the activation norms, specifically the attention and FFN inputs, across all the layers.
So what does running PCA on that unified data actually do for them?
It's like finding the central axis of a scatter plot of all the layer data at once. Applying PCA across the whole network gives you a single, consistent rotation matrix.
And that matrix projects the model's entire latent space into a lower dimensional one.
Exactly. It identifies the most important hidden dimensions to keep across the whole network simultaneously. That consistency is key for stability.
So it's a global optimization, not a local one. Okay, and finally, they tackle the biggest part of the parameter count with feed-forward pruning.
For that, they calculate an important score based on the averaged absolute value of the output of the gated linear activation expression. That's the W2 of PSI-LU of W1x times W3x.
So that score tells them which dimensions in the W1 and W3 matrices are contributing the most.
And consequently, which corresponding rows of W2 to keep. It lets them target the largest part of the network with very high precision.
Okay, so once they've done this very careful pruning, they move right into the distillation stage, which is the actual knowledge transfer.
Correct. And throughout the whole pre-training process, they use a forward KL objective, pure logic distillation. They found this simplified approach actually worked better than trying to balance it with a standard next token prediction loss. Simpler was better.
And the Mistral Small 3.1 parent model is the consistent teacher for all the stages and all the sizes during this foundational pre-training.
Yes. And remember that long context work. The pre-training is split into 2 phases. First, a short context stage at around 16K tokens, and then a long context stage that uses yarn and temperature scaling to push the window all the way up to 262K.
Okay, moving beyond the foundational pre-training, let's look at the specialized post-training variants. These are the ones people will actually deploy, the Instruct and reasoning pipelines.
Right, this is where they instill the really complex behaviors.
Yeah.
The Ministral Instruct pipeline is all about high-quality multimodal and text instruction following. It involves supervised fine-tuning, or SFT, followed by online direct preference optimization, ODPO.
Now, this is a crucial detail I want to underline. For SFT, they switch teachers. They distill from the much stronger Mistral Medium 3 model.
Yes, that teacher switch is a key feature of their success here. After that comes the preference tuning with ODPO, which is an online variant of DPO.
And the online part is key.
It is, because the process samples 2 responses from the current policy, and then it uses a pairwise reward model to dynamically rank them.
What's fascinating is how they refine the DPO loss. They're not just using hard win or loser labels, they're incorporating the probabilistic output of the reward model, plus stabilization tricks. It turns it into a much smoother optimization.
And practically, the online nature lets them do smart things,
No.
like automatically treating any response that gets stuck in an infinite loop as a loser. If you've ever fine-tuned a model that just starts repeating itself, you know how critical that is.
That's a great example of smart engineering in the alignment process. Okay, let's pivot to the Ministral reasoning pipeline, which is for complex problem solving. This is an intense 3-stage process.
It starts with SFT, but using extensive chain of thought, or COTE data. A diverse mix of math, coding, visual reasoning. But the smalls model, the 3B variant, it hit a snag here.
Right. Vanilla SFT made the 3B model unstable and way too verbose. It just couldn't handle the complexity of the raw COTE data.
So they had to use logic distillation from the even smaller Magistral Small 1.2 model just to stabilize it and get it ready for reinforcement learning.
A necessary detour.
A necessary detour. The main RL step is Group Relative Policy Optimization, or GRPO, done in 2 stages. First, STEM RL, focused on math, code, and visual reasoning. Then, General RL, which uses an LLM judge to improve general chat quality.
They also increased the max generation length to 80K tokens during RL. I assume that was essential for letting the model actually finish those complex multi-step problems.
You can't solve a hard math problem if the model stops generating halfway through. And the final step is applying ODPO again, post-RL, to polish conversational quality, but with a critical twist.
They stripped the internal thinking chunks before scoring.
Exactly. That modification is clever. It ensures the final polish focuses purely on the natural user interaction, ignoring the messy internal steps that are crucial for reasoning, but you really don't want to see in a chat.
Which brings us directly to the ablation studies, where they tested their assumptions, and they found a genuine paradox about knowledge transfer.
Yeah, the teacher paradox. This is probably the most interesting finding for researchers. During the pre-training stage, distilling from the stronger teacher, Mistral Medium 3, was consistently worse than using the less capable parent, Mistral Small 3.1.
Wait, so using the stronger teacher actively hurt them during foundational pre-training? That feels counterintuitive.
It does. It confirms this previously observed capacity gap. The theory is that the smaller student model's architectural capacity, its number of layers, hidden dimensions, it limits its ability to absorb the super complex knowledge from an overly capable teacher. The teacher's just too advanced.
So the student's architecture literally prevents it from efficiently decoding the knowledge from the teacher.
Precisely. However, the paradox resolves later. The models did benefit a lot from the more capable Mistral Medium 3 teacher during the post-training SFT and alignment phases. So it seems the capacity gap is mainly a pre-training phenomenon.
Another key finding was the Instruct advantage. They found that distilling from a post-trained teacher, like an Instruct variant, during the student's initial pre-training actually led to better performance.
This is significant. It implies that the preference-optimized logic that's already baked into a fine-tuned teacher provides a substantial lasting benefit, even before the student gets its own instruction tuning. You're giving it a head start on alignment.
Now let's circle back to that trade-off you mentioned with the reasoning models, the verbosity trade-offs. What were the unintended consequences of optimizing so hard for reasoning?
They found that aggressively incorporating long code data in the Instruct SFT stage, well, it improved STEM scores, which is great, but it came at a big cost to general chat usability.
And what did that look like in practice?
It resulted in this undesirable, unnatural chat behavior. The paper calls it excessive reflection, internal monologues, and backtracking behavior.
So you ask for a simple fact and you get a 5-paragraph internal debate before the answer?
Exactly. That would make a general deployment unusable. They give that example of the model showing its internal steps for finding the sum of integer bases. If you're just chatting, you do not need to see the math homework.
That makes perfect sense. So for you, the engineer deciding which model to deploy, knowing that trade-off is critical. Okay, let's look at the numbers. Did all this effort pay off?
Absolutely. The pre-training comparisons in Table 2 show that the Ministral 314B base model doesn't just keep pace, it actually outperforms Quinn 314B on benchmarks like Trivia QA and Math, all while being trained on a tiny fraction of the tokens.
And for parameter efficiency, the 8B model is the real star here. It's outperforming the larger Gemma 312B on most benchmarks. For anyone constrained on GPU memory, getting 12B level performance from an 8B model is a huge win.
The Instruct comparisons are even more compelling. Ministral 314B Instruct leads the pack in really critical alignment benchmarks like Arena Hard and Wild Bench.
Significantly beating strong competitors like Q3 and Gemma 3, it proves their alignment pipeline is just top tier.
And when we look at the specialized reasoning comparisons, the Ministral 3 variants show clear strength. They consistently lead their size-matched counterparts, particularly in really rigorous math competitions like AIM and HMMT.
Even the smallest 3B reasoning variant is still competitive, surpassing Quen 3 VL4B on several math benchmarks. That's a testament to how effective Cascade Distillation really is.
And we have to revisit that final ODPO polish on the reasoning models. Because reasoning-optimized models can be pretty bad at conversation, that final step was essential. It delivered huge gains on alignment benchmarks, effectively closing that conversational gap.
So to summarize for our listener, Ministral 3 delivers a complete, high-performing family of 9 models. It proves you can achieve competitive, state-of-the-art AI capabilities under tight compute and memory constraints by using strategic, iterative distillation.
It clearly shows a viable, resource-efficient path forward that doesn't just rely on throwing petascale token counts at a problem. But the most provocative finding is still that teacher paradox.
The idea that stronger teachers aren't always better for the pre-training stage.
It suggests there might be an underlying architectural mismatch, a capacity constraint that we're still missing when we try to optimize knowledge transfer. It's not just about the data, it's about the shape of the model receiving the knowledge.
Exactly. So if you, the developer or researcher, are designing a smaller student model, how should you adjust its intrinsic architecture, not just parameters, but maybe attention mechanisms or layer configurations to bridge that capacity gap? How do you let it fully leverage the immense knowledge stored in the largest, most capable teacher models available?
That's the key research direction this paper really opens up for the community.